Hello and welcome. In this video, we're going to talk about what differentiability is and where functions are differentiable or not differentiable. We're also going to learn a shorter way to find the derivative of a function at a particular point called the alternate definition of derivative. So our goal in this lesson, I can determine where a function is differentiable and I can find the derivative using the alternate definition. Let's go ahead and jump right in. So in the last video, we talked about the slope of the tangent line and how that is called the derivative. So we can find that function for different values. However, there are certain places that functions are not differentiable. So differentiability or differentiation is a term for finding the derivative. And a function is not always differentiable everywhere. So let's talk about where it is differentiable. A function is differentiable if the derivative exists at that given point or on that given interval. What this means, if we tie it back to limits, is that the limit from the right is the same as the limit from the left is the same as the derivative evaluated at that particular value. So this feels a lot like continuity. A function must be continuous in order to be differentiable. So let's write that down. And if we look at the limit from the right and the left, that's the same as just evaluating the derivative at that particular value. Now, this idea of looking at this from the limit perspective, this is going to come into play once we learn some other strategies for finding derivatives besides the limit definition. So what we're going to focus on here is just how do we look at a graph and identify where a function is differentiable and where it's not differentiable. So there's three reasons that a function may not have a derivative at a particular value or over a particular interval. The first is that it's not continuous. And we know a variety of reasons that something might not be continuous. It might not be continuous because of a hole, because of a vertical asymptote, or because of a jump. Regardless of how it's not continuous, if a function isn't continuous at a particular value, it's not differentiable at that value. The second reason is a sharp turn. And again, we'll define this more when we start looking at this from the perspective of an equation and not just a graph. But if we're coming in and the derivative is changing direction really quickly, the best example of that is an absolute value at the vertex of an absolute value curve, then that function is not differentiable. So if it's changing what it's doing really quickly, we call that a sharp turn. That isn't going to give us a differentiable place on the function. It's not going to be differentiable at that value. And lastly, if there is a vertical tangent, that would mean that the slope is undefined, right? If I had a function like this and I was trying to write the equation of a tangent line right here, it's not perfectly drawn, but if that tangent line is vertical, then the slope would be undefined. And if the slope is undefined, the slope is the derivative. That would mean the derivative would be undefined. So places where functions don't have derivatives, discontinuities, sharp turns, and vertical tangents. Let's go ahead and look at some of these visually. All right, so here we have 5 graphs, each of which has an issue at the value of x equals 1. So I want you to look at that list of 3 reasons and identify for each of these 5 questions why it's not differentiable at x equals 1. All right, hopefully you had time to do that. What I want you to notice on A, B, and C is that they are not continuous at x equals 1. Here there's a hole, here there's a jump, here there's a vertical asymptote. And because they're not continuous or because they're discontinuous at x equals 1, they're not going to be differentiable there. Part D has a sharp turn, so it would not be differentiable at x equals 1, and part E has a vertical tangent, and that's why it would not be differentiable at x equals 1. So again, we're going to build on this idea of differentiability and how to look at this from the perspective of an equation or a function in a later video. Let's go back now to what we learned in the last video about derivatives using the limit definition, and let's extend that to a faster, more efficient way to find the derivative at a particular x value. Okay, one thing I want to point out is that we're about to talk about something that only works if we're finding the derivative at a particular number, and that's really important. If we were being asked to find the derivative as a function, as of right now, we'd have to go back and use the limit as h approaches 0 of the difference quotient. This strategy for the alternate definition works if we're looking at a particular value. And here it is. Instead of taking the limit as h approaches 0. We're going to take the limit as x approaches the value that we're trying to find the derivative of. So in this example here, we're going to take our c would be 1. We're going to take the limit as x approaches 1. We're going to take the limit of the original function, still with x, minus what we get when we plug c into the function, all divided by x over c. And again, we're going to have to use different strategies that we've learned previously, possibly factoring or trig, in order to simplify this limit. So let's go ahead and look at this example. F prime of 1 is going to equal the limit as x approaches 1, as x approaches c, of f of x, which in this case is x squared minus x, minus f of 1. So I'm going to plug 1 in, 1 squared minus 1 to both of my x's here, all over x minus 1. Let's go ahead and simplify. This is going to be the limit as x approaches 1. This is going to be 0 over here. 1 minus 1 is 0. So this is going to be x squared minus x minus 0, or x squared minus x over x minus 1. Now I can't use direct substitution because I would get indeterminate form. So I'm going to go ahead and factor the numerator. The numerator, both terms have an x in them. So I can factor that out, and then I can simplify this factor. So now I just have the limit as x approaches 1 of x. Well, I can do that. I can plug 1 in there. This means that f prime of 1 is equal to 1. So this is a little more efficient than having to deal with expanding a function out if you're using the limit definition as opposed to the alternate definition. However, you could use the definition we learned in the last section and expand it out, and then once you have your function, you could just plug in the specific x value that you're looking for. Let's look at a couple more examples. All right, here we go. So we're going to look for f prime of 6. This c equals 6 is telling us we want to find f prime of 6. That means we're going to take the limit as x approaches 6 of f of x, which is the square root of x minus 2, minus f of 6, so I'm going to plug 6 in, over x minus 6. Let's go ahead and simplify the numerator. This is going to be the square root of x minus 2 minus the square root of 4, which is 2, over x minus 6. Right now, we can't use direct substitution because if we plug 6 into the numerator, we get 0, and if we plug 6 into the denominator, we get 0. That means we need to use a strategy from chapter 1, like conjugates, since I'm seeing that radical, in order to be able to evaluate this limit. So in the numerator, now I'm going to have x minus 2 minus 4 over the x minus 6 that was already in the denominator times this conjugate, x, the square root of x minus 2 plus 2. Well, x minus 2 minus 4, that is x minus 6, so these are going to divide out. So I'm going to have the limit as x approaches 6 of 1 over the square root of x minus 2 plus 2. And now I can actually just plug in 6. That's going to give me 1 over the square root of 4 plus 2. So 1 over 2 plus 2, f prime of 6 is going to equal 1 over 4. All right, let's look at another example. All right, this one has a little fraction work, but I think you can handle it on your own. So why don't you pause the video and see how far you can get on your own, and then unpause the video and see how you did. So here's the setup. I'm going to need a common denominator, so I'm going to multiply this fraction by 2 over 2 and this fraction by x over x. So that's going to give me 2 minus x over 2x, and notice this double negative is going to become a positive in the numerator. This whole thing is over x plus 2, but I would rather not have a fraction in a fraction, a complex fraction, so I'm going to just write times 1 over x plus 2. And I apologize, this should also be a plus, right? 2 plus x. Now 2 plus x and x plus 2, that's the same thing. So I can simplify that, divide that to be 1. So this is going to equal the limit as x approaches negative 2 of 1 over 2x. And I can plug negative 2 in there. That's going to give me negative 1/4, or 1 over negative 4. All right, let's look at just one more, and then we'll wrap up this video. That's right, I did it. I brought trig in here. So set it up and see how far you can get. And if you get stuck, unpause the video and walk through it with me. It's never as bad as it looks. So the limit as x approaches 0 of sine of x minus sine of 0 over x minus 0. Well, sine of 0 is just 0, and x minus 0 is just 0. So I have the limit as x approaches 0 of sine of x over x. And that's one of those properties we're supposed to have memorized, that is equal to 1. So f prime of 0 is equal to 1. Let's go ahead and wrap up this video. All right, in this video, we talked about what it means for something to be differentiable and the fact that a function won't be differentiable if we have a discontinuity, a sharp turn, or if we have a vertical tangent. Then we talked about the alternate limit definition of derivative, which allows us to find the derivative at a particular point. So we don't get a function out like we did with the regular limit definition of derivative, but we could evaluate the derivative at a particular x value. So our goal, I can determine where a function is differentiable, and I can find the derivative using the alternate limit definition. Go ahead and write down any questions, and I look forward to supporting you on this. Thanks for listening.